I wanted to end up with just a few comments on the assignment that you'll do for this material in this class. So in this assignment, you're asked to use the NumPy random number generator, and you're going to use it for two purposes. So one of them is to calculate a mathematical geometrical constant pi. And the other one is to calculate the volume of not a three-dimensional sphere, but a four-dimensional hypersphere. So we're going to do those two tasks in this assignment. And so let me just say a few words about calculating pi and calculating the volume of the hypersphere. So we're going to calculate pi by imagine a circle. Imagine a circle centered at the origin, and imagine that circle has a radius 1. So, we know the area of that circle. It's the area of that circle is, I almost forgot it, is pi r squared. So we know the area of the circle in terms of pi, the geometrical mathematical constant, and the radius of the circle. And if we think of a circle of radius 1, the radius of this the area of the circle is therefore pi. So we know the area of the circle. I can throw random numbers into now this two-dimensional space, random points into this two-dimensional space. And in that way, similar to how we calculated the volume of the sphere, we can calculate we can actually calculate the volume of the circle. And so we'll calculate a number that is the volume of the circle. And then if we know that the volume of circle is given by pi, that number will allow us to determine pi. So we're really turning around the calculation of the volume of the sphere problem on this calculating the surface, the area of a circle problem. We're going to turn it around and use it to determine the math constant, geometrical constant pi. So that's what you're doing the first example. You're actually interpret your results from calculating the area of the circle as a determination of pi. So in the second part of this problem, you're going to calculate the volume of a four-dimensional hypersphere, just like in the class material, we calculated the volume of the three-dimensional ordinary sphere. And you're going to do it by throwing random numbers. Now, the difference is for the three-dimensional sphere, we threw 3 random numbers for the x, y, and z coordinates, components of a point in space. And then we tested whether that point in space was either inside the three-dimensional sphere or outside the three-dimensional sphere. And we tested it by squaring the x, the y, and the z components and seeing whether they're less than or greater than 1. You're going to do exactly the same procedure for the four-dimensional hypersphere. So the four-dimensional hypersphere lives in 4 dimensions. We could call those dimensions, I'm going to add one. I'm going to call dimensions v, x, y, and z. I'm going to throw points into that 4-dimensional space. That involves generating 4 random numbers for each point, the components v, x, y, and z. And then if I sum the squares of the 4 components, the v component, the x component, the y component, the z component, see whether that's less than or greater than 1, that will tell me whether it's the point is inside or outside the hypersphere. And then by counting the fraction of points that are inside the hypersphere compared to the total number of points, just like we counted the number of points that were inside the ordinary sphere compared to the total number of points, we can calculate the volume of the hypersphere. In the case of the ordinary sphere, we knew the answer, 4/3 pi. In the case of the hypersphere, you probably don't know the answer, so you're going to discover that.